Pooja does always make me laugh with this video, Pooja.
Let me see it. Let me see it. Let me see it, Mom.
Yep.
What's that? I can see it. I can see it.
There's only 4 of us.
No, leave your phone. Come on, go drop it off. Alright.
Right, so good morning again. So this is just a makeup class for the class that we missed last week. So in this class, we're gonna look at statistics and probability. First, we're gonna look at statistics, right? So what is statistics? Statistics is a branch of mathematics that is used extensively in the real world to make decisions. Such decisions are made by gathering information, analysis, and making predictions. Now, statistics equipped us with tools to carry out investigations in a systematic way and to arrive at a solution based on informed judgment. That's basically what statistics is. Now, before we get into statistics, you have to understand the jargons or the phrases or terms that are used in statistics, right? So we're going to start off with simple statistics and population parameters. So let me give you a scenario here. Suppose we wanted to investigate the attitude of Form 5 students to mathematics. It will indeed be desirable to ask every student in Form 5 about how they feel about mathematics. However, this approach will be time consuming, it will be costly, and logistically challenging. On the other hand, one can obtain information as well as chosen subsets of the Form 5 population and draw valid conclusions about how students feel about mathematics. Okay, so the set of all Form 5 students is an example of a population. So for example, all the students of CTS College as well, this is an example of a population. All the citizens of Trinidad and Tobago, this is an example of a population. All the citizens of Guyana, that's a example of the population of Guyana. Now, while the subset of participants chosen to be interviewed is an example of a sample, right? So, for example, we're talking about, well, we're in the COVID situation right now, right? So the entire of Trinidad and Tobago will be the population. The sample will be the persons who are infected with the virus. Yeah, that will be a sample. Everybody following?
Yes, sir.
All right. So if data is collected from every person or object in a population, we refer to it as a census, right? Census is taking into consideration everybody in the population. So let's say the government wants to conduct research on the entire population. It will now be called a consensus. When they are drawing their conclusions, it will be from the consensus, which is from every single person within the population. Yes? So population parameters now. What are population parameters? They are measures associated with a population. This would include the mean score in mathematics, right? And the proportion of students who like mathematics, we call it, let's just say P. Now, since it is almost impossible to collect data from all members of a population, these measures are not exact, okay? So let's get into it. To obtain estimates of population parameters, we obtain statistics from a sample of the population. This would include the mean score of a subset of the population in mathematics. Now, we can call this bar X. That symbol is represented as bar X. And the proportion of students who like mathematics, right? So we summarize, we analyze, and calculate measures of data from a sample. This is called descriptive statistics, right? We actually describe stuff. When we use our sample data to make predictions about a population, such techniques are called inferential statistics. You understand the difference between descriptive and inferential statistics? Descriptive statistics is when you summarize and you analyze and calculate measures of data from the information you would receive from the sample. And when you use your sample data, that is the data that you collect from the population to determine, when you use that information to predict certain patterns about the population, that will be referred to as inferential statistics. So for example, let's say you're conducting research on diabetes in Trinidad, and you of course conduct research, and you from your sample or your population, you say that because of the eating habits of Trinidadians and Tobagonians, you can clearly see here that there will be an increase in diabetes cases, etc. That is referred to as inferential statistics, when you are making a prediction about a population based on the information that you would have gathered from that sample. So let's get into it. Types of variables. The type of variable we collect will depend on the characteristics that we are investigating. We may be interested in the mass of a newborn baby. You might be interested in test scores, the type of transportation, or the opinions of persons on a social issue. Each characteristic is associated with a variable to be investigated. So what is a variable? A variable is any characteristic whose value may change from one object to another, to the other in a population. Now, variables can be qualitative, which is non-numerical, or quantitative. Now, a lot of students do not understand the difference between quantitative and qualitative. Qualitative data will be data that you cannot measure. So, for example, let's say you are interviewing somebody on how they feel about the COVID situation. You cannot measure. There is no tool, no mathematical tool or scientific tool that can measure how a person feels, right? That information, you cannot measure it. So there is no quantifiable data there. That would be referred to as qualitative data. You cannot assign a numerical value to how somebody feels, right? So feelings are an example of qualitative data. You cannot measure that, all right? You can try to quantify it, but you cannot give an exact measurement of it. That's qualitative data. Quantitative data, on the other hand, is when you can actually measure something. So for example, let's say you have a fever. You can actually take your temperature and actually measure it. It's quantifiable, so you can assign a numerical value to it. Yes? You all think you understand the difference between qualitative and quantitative? Yes, no?
Yes, sir, I understand.
All right. So qualitative variables are usually categorical in nature. So some examples of categorical data are shown below. Gender, for example, has only two possible categories and is called a binary variable. Other variables have at least three categories. So let's look at some of the qualitative variables. So gender, we have categories such as male or female. We have ice cream flavors such as vanilla, cherry, soursop, chocolate, whatever. Then we have types of transportation. The categories will be bus, train, cars, etc. Budget expenditure, you can spend money on food, rent, transportation, etc. Months of the year, the type of car, the color of shirt, etc. Yeah, these are qualitative variables. Now, in quantitative data, the value of the characteristic is a number. So remember I told you all you assign a number or quantitative value to it. You can actually measure it or assign a numerical value. This is basically it. So for example, the number of children in a family, you can actually count that. You can assign a numerical value to that. So the family has 2 children, 3, 1, 4, 5, a million, etc. Yeah? You can actually measure the size of somebody's shoe, the height of a person. All of these will be quantitative data, right? So numerical data can be of two types. It is discrete if it can only take particular values within an interval. Examples of discrete data are given in the table below. Notice that there are no values between any two consecutive values. So the number of items correct in a test, we have the person could get 0, they could get 1, they could get 2, they could get 3, they could get 4 right, they could get all correct, etc. Shoe sizes can be 2, 2.5, it can be 3, 3.5, it can be 4, 4.5, etc. Number of groceries in a city can be 30, it can be 32, it can be 60, etc. Number of Skittles in a pack, 50, 51, 53, etc. And well, you all get the idea, right? So that is referred to as discrete data. Discrete meaning that there is no in-between numbers. A continuous variable has an infinite number of possible values between any 2 points on the measurement scale. Measures of distance, weight, temperature, time are examples of continuous variables. Some of these are shown below. So the height of seedlings in a sample So that seedlings is like when you plant a little seed, right? Obviously, and a grain. So some possible values could be in centimeters, 4.5 centimeters. It could be 5 centimeters. That could grow to 6.1 centimeters, then 7.3 centimeters, then it could be 8.0 centimeters, etc. You notice here that there is no consistency with it. Here you are still seeing 50, 51, 52, 53, 30, 32, 60, etc. Right? 2, 2.5, 3, 3.5, 4, 4.5, etc. There was still some consistency, and obviously, there is only a certain number of skittles that can be in a pack, right? And a certain number of floors a building can have a certain size of shoes. You ain't going to see somebody with a shoe size 27 and then somebody with the next shoe size 37, right? So that's the difference between discrete data and continuous data, continuous variable. It actually increases or decreases, right? It continues. So temperature of a mixture, it can be 45.3 degrees, sorry, 0.23 degrees, it can be 46.45 degrees, it can be 47.78 degrees, it can be 50.04 degrees, etc. Okay? Now, with continuous variables, the exact value of the measure is not possible to determine, which is basically what I was saying here. Our degree of accuracy, which is how correct the information is, it will depend on our measuring devices. So for example, your temperature, sorry, your thermometers, etc. So for example, a mouse weight will have an infinite number of possible values between 25 grams and 26 grams, because one could always add extra decimal places to the measurement. Now, while it is possible to summarize, represent, and analyze data collected on variables that are either quantitative or qualitative, it must be noted that the techniques used for qualitative data will differ or will be different from those of quantitative data. Obviously, because one deals with, because of the interference of discrete and continuous data, right? Which is what I just explained. So let's see here. To explore these differences more closely, we consider the following example comprising data collected in 5 variables from a group of 40 students in a graduating class. So as you can see here, we have gender being male or female. We have their meal preferences from vegetarian, chicken to fish, etc. Then we have their hat sizes from extra small to extra large, etc. Then we have the gown sizes and we have their heights. As you can see in this entire table here, I will send you all this handout as soon as I'm finished, right? So you will be able to take a better look at it. So these are the data that we can pull from it. Of course, you have your legend here, right, which will explain more or less what you are doing in the variables that you are using. We define them to the bottom here, right? So now we can summarize the variables. So gender, it's qualitative and categorical. So we can, for the values, we can have male or female. We have gown size, it is also qualitative, and we can categorize it in terms of extra small, small, medium, large, extra large. Then we have meal preferences. This is qualitative, so we can also categorize it. So vegetarian, chicken, fish. Then we have height. Height is therefore quantitative, not qualitative. It is quantitative and it is therefore continuous. So the person's height are between 150 to 179. So the shortest person is 150 and the tallest person is 179. Then we have the ring sizes. It is quantitative data because we can actually assign a value to it and it is discrete. So it doesn't change. So we have 3.5, we could have 4, 4.5, 5, 5.5, etc. Everybody okay? Any questions so far? You have any questions?
No, sir.
All right. So let's deal with frequency distributions now. Data that is not processed or organized is called raw data. So obviously when you go to collect data, let's say some of you were doing your SBA, those of you who are actually in school and doing your SBA, right? you would have collected data from the population that you would have been studying, the sample that you've been utilizing, right? Now the data that you collect there, that's raw data. Let's just say you send out a questionnaire. The information that you collected from the questionnaire without actually tallying anything, that's the raw data that you are collecting, right? So the data shown in the above table is the raw data collected from 4 variables. Now it is difficult to draw conclusions from raw data by simply looking at the values. A common method of organizing raw data is to construct a frequency distribution. This is usually the first and simplest step in analyzing data. So ungroup frequency distributions, what is that? A frequency table is used to summarize a set of data. It records the frequency or number of times each value occurs. There are usually 2 columns in the table. The first column lists the set of possible scores, while the second column records the frequency of each score. So let us see what I have here. So we have gender. How many males were there? There were 19 males. How many females were there? There were 21 females. So the total number of students would have been 40. That's the first thing you have to do. Then we can construct a similar frequency distribution for meal preferences. So how many students wanted vegetarian? We can count, we can see from the table 5. How many students wanted chicken? 19. How many students wanted fish? 16. And of course the total must be 40, because if you're catering for 40 students and you get 41 here or something, you know something wrong somewhere, right? Now we can tally this. We can do a tally for either one of them, right? But in this case, we'll do a tally for the hat sizes. So how many students wanted extra small? 8. And of course, we know when we are drawing a tally, it's 1, 2, 3, 4 strokes, and the 5th stroke goes across. And then we start a new one. So this represents 5, and 6, 7, 8. Next one, the amount of students who wanted small, it will be 11. So let's count 1, 2, 3, 4, and then 1 goes across to represent 5. 6, 7, 8, 9, and 1 goes across to represent another group of 5. So that's 10, and 1 makes 11. The other one is 12. So we know we'll have 2 groups of this, and then 2 extra strokes. This one is 5, so it's just 4 with a cross on it. And next one is 4, so we just draw in 4 strokes. Okay? And of course, your total, when you add it up, you must get 40. Your data must be consistent. Let's look at grouped frequency distributions now, or discrete data. So the data on gown sizes has 15 possible values, and if represented in an ungrouped distribution, there will be 15 rows. This will not permit meaningful results, and is better to group the data so we can reduce the number of rows. We can select 5 classes, each containing 3 values. Let's see, 20 to 28. We can do 31 to 33, 34 to 36, 37 to 39, 40 to 42. Yeah? So let's see now. How many students required a gown with the size 28 to 30? The number is 8. Those who requires a size 31 to 33 will be 12 students, 34 to 36, 11 students, 37 to 39, 5 students, 40 to 42, 4 students, and of course, when you add up your total in the frequency, you must get back 40. Any questions so far before I move on? You all, any questions?
No, sir.
All right. All right, so let's look at grouped frequency distribution or discrete data. In tabulating grouped data, we form classes or groups to accommodate all the raw data. The class limits specify the range of data values that fall within a class. So class limits are defined as a minimum and the maximum values the class interval contains. Now you must understand this, right? So for you to understand that, you must understand the lower class limit and the upper class limit. So for example, for the class 150 to 154, the lower class limit, which is LCL, is 50, and the upper class limit is 154. So it was mentioned earlier that for continuous data, the true value of the measure is not really known due to the lack of precision in measuring instruments. So for example, the class 150 to 154 will have height rounded to the nearest centimeter and can actually contain values from 149.5 and up to values not including 154.5. So in other words, if you have the lower class limit here, you always go 0.5 less, and the upper class limit here, you always go 0.5 more. You all follow? Yes, no?
Yes, sir.
All right. So the 0.5 values, which is the 149.5 and the 154.5 values, will be referred to as the endpoint or the class boundaries. So in the first interval, 149.5 is actually the lower class boundary, and 154.5 is the upper class boundary. These class limits and class boundaries for the data on the height of students are shown in the table below. So we have the height of the students here, right? And we list all of the heights that we were using here. Now, X will represent the data, and it can be between 149 to 154. You're seeing that? Yes? No?
So I think you need to explain back everything.
Everything as in everything in the handout?
No, sir, just the last, the table there.
Okay, there's just this table, right? Okay, so remember I told you all the lower class boundary will be 0.5 less than whatever you have here, and 0.5 more than this upper class boundary here. So 150 take away 0.5 will give you 149. 154 plus 0.5 will give you 154.5, as you can see here. 0.5 less than 155 will be 154.5, which is this one here, and 0.5 more than the upper class boundary will be 159.5. 0.5 less than 160 is 159.5. 0.5 more than 164 is 164.5, which is what we have here. You see it?
Yeah, so I understand, but the frequency, that is just separate that up to the 40.
Yeah. This is how many people were of height 150 to 154, 6, 155 to 159, which is 5, 160 to 164, which is 7, 165 to 169, which is 9, 170 to 174, which is 8, 175 to 179, which is 5 persons, and you add up all of the persons in the frequency, and you are supposed to get back 40. Yeah?
Thank you, sir.
No problem. You understand it?
Yes, sir.
You sure?
Yes, sir.
All right. So displaying the data now, of course, you all don't have to worry too much about the Excel sheet. So let's just say how you can, let me just explain to you how you can display the data. You can display the data on a pie chart. A pie chart is, we mostly use it when we want to make basic comparisons to show how you can compare smaller segment or smaller sectors to the entire population, right? So it is used usually for representing categorical data when the number of categories is relatively small. So most of you would have used pie charts, etc., when you would have been doing your SBAs in school and whatnot, right? So let's see here. Now remember, it's a circle we are dealing with, and of course, we know the angles in a circle are at 360 degrees. So let's say you are doing a pie chart for the number of males and females. So we know it was 19 males out of the 40 and 21 males out of the 40. So if you want to represent how much of the circle males will pick up in terms of degrees, it will be 19 males out of the 40 multiplied by 360 degrees, which will give us 171 degrees. So this blue section here is really 171 degrees. Of course, you would use a protractor to do this if you had to manually draw a graph, a pie chart, right? But in the exam, you don't have to worry about that. I've never seen when they ask you to draw a pie chart, okay? Next, female will be 21 out of the 40 multiplied by 360. This will give us 189 degrees. Any questions there? This orange part here will represent 189 degrees, okay? Well, since there are no questions, let's go on to bar charts then. So what is a bar chart? Bar charts or bar graphs are used to display data when the values or the variables are discrete. Variables can be categorical or numerical. The bar graph has the following characteristics. Firstly, the spaces between the bars, it must be equal. The width of the bars are the same for all of the bars. So you can't have one bar the size of your finger, and then a next bar the size of 3 of your fingers, and then the next bar the size of 2 of your fingers. You cannot be inconsistent, right? And the spaces between each bars, again, it must be equal. Now, you don't have to worry too much about remembering this, because thankfully this year, it's a multiple choice, yeah? So the height of the bar gives the frequency. The bar chart is best drawn on a grid, and the bars can be drawn horizontally or vertically. So let's see here. So we can use the bar chart to represent the students' meal preferences. So we have vegetarian, we have chicken, and we have fish. Of course, as you can see, the bars are the same width, and the space between the bars are all equal. This one not this length apart, and this one quite down here, right? Equal lengths between the bars. And of course, the vertical axis tells us the frequency. The frequency is always on this axis here, okay? Provided that the bar graphs are vertically drawn. Any questions here? So anybody can tell me how many students prefer vegetarian food?
Yes, sir.
How much?
5.
Yes, and how many preferred chicken?
19.
And how many preferred fish?
16.
Correct, right? So we're reading off from the frequency here. So between 4 and 6 is obviously 5. Between 18 and 20 is obviously 19. And then of course this is on the line itself, so this reads off to 16, the frequency of students who wanted fish, chicken, and vegetarian food. All right. Hat sizes. Somebody else besides Shishmita want to tell me the sizes of the hats?
So
The extra small is 8. The small is 11.
Yeah.
The medium is 12. The large is 5, and the extra large is 4.
Correct. So let's move on to histograms now. Histograms are used to display continuous data and are useful in showing the shape of a distribution. It resembles a bar graph, except there are no gaps or spaces between the bars. This is because the histogram represents data in which the values or the variables are continuous, and as such, variables can take any value in the interval on the horizontal axis. So where one bar ends, the other one starts. So in constructing a histogram, upper class boundaries are plotted against the frequency. So remember, we found the upper class boundaries, right? Remember, we just add 0.5 to the upper class boundary. How do we find the lower class boundary again? Anybody can tell me? Anybody? Sanjay, the class is until 12. Anybody want to tell me how we can find the lower class boundary? I told you all that before. We subtract 0.5 from the lower class boundary to get the lower class boundary. For the upper class, we add 1 to it, okay? So remember I told you all the histogram represents continuous data and there are no gaps. So let's look at a side-by-side comparison of a bar chart and a histogram. Now, although they are similar, they are not the same, right? The histogram represents continuous data. So where one boundary ends, the other one begins. Are you all seeing it? And you notice what we are using here, right? The boundaries only. So 149.5, 154.5. 159.5, 164.5, etc. Any questions there?
No, sir.
Okay. Frequency polygons. If the midpoints of the bars of a histogram are joined by straight lines, a frequency polygon is formed. Just like a histogram, the frequency polygon is useful in displaying the shape of a distribution. In a frequency polygon, we plot the midpoints of the class interval against the frequencies. Using the data on gown size in table 3, we will now draw a frequency polygon. First, we must obtain the midpoint of each class interval. We calculate these using a half or 0.5 multiplied by the upper class limit plus the lower class limit. So let's see here. What is the upper class limit in this case? Anybody? What is the midpoint then? Earlier.
For the grid size, sir?
Yeah. No. The midpoint. What would be the midpoint here? What is the midpoint of 28 and 30? What is the value that is dead center in the middle of them?
29?
And how did we get 29?
29 is between 28 and 30, half of it.
Right. And then 31 and 33.
32.
And well, it's obvious right there, it's on the screen, right? And of course, the frequency is the same what we get from the table, right? Yeah. Can you all answer so I will know that at least you all are following?
Yes, sir.
Thank you very much. Right. So this is the information that we will be using to plot the frequency polygon, as you can see here, right? These are the gown sizes in terms of the midpoint. And of course, we have from 0 to 14 going up here. Yeah? Any questions?
No, sir.
Okay, we will not be doing line graphs and stuff because I've never seen it really being tested. So I'm not going to waste time to do that, right? I haven't seen these things either. Right. So obviously the things that I don't go through, you all can go through it yourself, right? I'm just going through the things that I know for sure are tested, okay? So let's look at measures of central tendency. This is definitely tested in the multiple choice. Yeah? So what are measures of central tendency? Measures of central tendency are one such measure, and there are 3 of these: the mean, the mode, the median. Anybody have any questions about those? You would have been doing these since primary school, right? So the mean is also referred to as the arithmetical average. Now, how do we find the mean? Anybody, before I go into it? Look at it right here. We add up all of the scores and divide by the total number of scores. So you add up all of these here, and then divide by the number of scores. So how many scores are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I want somebody to tell me the mean of this set of scores here. Who's going to tell me?
I get 12.7.
12.7.
Yeah.
Yeah. Those of you who are confused, look the work in here. Just give me a minute while I call the roll, right? Right. So yes, we add up all of the values. Of course, you can represent the mean as X bar, which is what I told you all. This is the symbol for it. So you just add up all of them, and you will get 127, and you divide it by 10, which is the number of scores, and you would have gotten the mean. Right? 1, 5. Sorry, on 5 chemistry tests, John received the following scores. He got 72, he got 86, he got 92, he got 63, and 77. What is his mean score on the 5 tests? So again, we add up all of them. So 72 plus 86 plus 92 plus 63 plus 77 will give us 390. And of course, we divided by how many tests he took, which is 5. And we would have gotten 78. So the mean score of all of his tests would be 78. Now, part 2. What test score must John earn on his 6th test so his mean score for all 6 tests will be the same? Let's take a look here now. So remember I told you we got 78, right? So since his average on all 6 test scores is to be 80, then the sum of all the scores on the 6 tests is 80 multiplied by 6, which is 480. Not so? Now the total must include the sum of the scores on the first 5 tests together with the score on the 6 tests. So the score on the 6 tests should be 48, take away the sum of all the 5 tests here, right? Which will work out to be 390, which is what I explained to you all before, as we can see here. So 480 take away 390 will be 90. So the score of the 6th test should be 90. Any confusions? Anybody want me to re-explain anything?
No, sir.
All right. Okay, the median. How do we find the median? To find the median, whatever the numbers are that you are given, you arrange them in either ascending order or descending order. You choose your preference. And the value that is in the middle will be the median. Now, if there are 2 values in the middle, you add the 2 values and then divide by 2. So let's see here. Determine the median of the following sets. So first you arrange the scores in either ascending or descending order. In this case, they arrange it in ascending order, right? So they rearrange this to 0, 3, 4, 5, 6, 7, 7, 8, 9. And the number that is dead center is 6. So 6 here is the median score as it divides the set into 2 equivalent sets with 4 members on each side. So on the right-hand side of 6, we have 1, 2, 3, 4 members. On the left-hand side of 6, we have 1, 2, 3, 4 members. Any questions there?
No, sir.
Okay, I'm giving you all 3 minutes to try this one here for me. Just excuse me for a minute, I need to get some water. Anybody got it? Anybody?
Is it 16.5?
No, Emily, that's incorrect. Yeah, Nitu, your answer is correct. So we arrange them in ascending order or descending order. Let's see. Our ascending order, we have 16 and 17. We have 16 and 17 in the middle here. So we add 16 and 17 together and we divide it by 2 and we will get 16.5. So the median here is 16.5. Yeah, there are 2 16s. Okay, so the properties of the median and stuff, you all could read that in your own time. So the mode, what is the mode? The mode is the most frequently occurring value here. So what value occurs the most here? Anybody can tell me? Correct, 19. So 19 is the mode because it occurs the most, right? So what is the mode here? In example 8. 3 occurred how many times? 1, 2, 3, and
3
5.
and 5.
Correct. 5 also occurred 3 times. So 3 and 5 are the mode because they occur the most. Yeah? Of course, you all can read the properties of the mode, the median on your own. It's nothing too difficult to read. Right, let's look at the median, the mean, and the mode from a frequency table. So the score of students obtained from tossing a die, the scores obtained from tossing a die, a total of 40 times, are recorded in the table below. So 1 occurred 8 times, 2 occurred 5 times, 3 occurred 9 times, 4 occurred 6 times, 5 occurred 7 times, 6 occurred 5 times. Okay? Now, from this data here, I want you all to tell me what you all think would be the most occurring number. Three, correct. 3 is the most frequently occurred number because it came up 9 times out of the 40 times, right? It came up the most amount of times. Yeah. Now to obtain the mean score, we need to calculate the sum of all 40 scores, since the frequency tells us how many times each score occurs. We can obtain the total for each individual score by multiplying each score by the frequency. So these are the number of faces of the die. Remember, die has 6 faces, right? A 1, a 2, a 3, a 4, a 5, and a 6th face. This is how many times that they occurred. So to get the frequency, we multiply. So 1 by 8 we get 8, 2 by 5 is 10, 3 by 9 is 27, 4 by 6 is 24, 5 by 7 is 35, and 6 by 5 is 30. So the total sum of f of x is 134. And of course, the mean is 40. Any questions so far?
No, sir.
So if we want to find the mean, how are we finding the mean? Based on that information here, how do we find the mean? Anybody want to tell me?
So
Uh-huh.
you divide it by the amount,
You divide what?
how much you add up by how. Oh,
No, tell me the actual value.
Oh,
Which is what divided by what, Emily?
this one. So 6.6.
How you get 6.6 now?
Because I do from the total number of frequencies it had and then divide it by how much it had.
Tell me in terms of values, not words. All they have to do here, people, is just divide 134 by 40, you know, and you get a mean.
Oh, okay.
Yeah. So if you're given a score, in this case it's the die, right? And a frequency, again, you just multiply it to get f of x, and then you divide that amount by the total number of attempts, which is in this case 40. Yeah, the total frequency. Understood? Yeah, Emily, you are correct. And this is the answer right here. So 134 divided by 40 will give us 3.35. Yeah, or if you want to put 3.4 to 1 decimal place, that's fine. The mean from grouped frequency distributions. When data is grouped, it is not possible to reconstruct the raw data. Hence, we cannot obtain the exact value for the mean. However, it is possible to obtain a very good estimate of the mean using the following method. So consider the following data in which the masses of peas were recorded. So the mass in grams of 3 peas is between 3 to 7 grams. The mass of 8 P's is between 8 to 12 grams. Of 12 P's is between 13 to 17 grams. Of 10 P's is 18 to 22 grams, and so forth. So how many P's did we weigh? Obviously, we weighed 40, right? As you can see there, the total is 40. Now, we know that 3 P's had masses that were between 3 to 7 grams. This means that their masses could have been 3, 4, 5, 6, or 7 grams because it's 3 to 7. To obtain the total mass of the 3 P's in this interval, assume that the average mass, is 5 grams, and we multiply 3 by 5 to obtain the mass, the total mass of 15, because remember, it's how much, which is in this case 3, which is the score, by 5. You all following? And we get, well, obviously 3 by 5 is 15, etc. Let me use the table to make more sense, right? So the midpoint of 3 and 7 is 5, of 12 and 8 is 10, right? Of 13 and 17 is 15. If you can't see it, you just add them, the upper and the lower, and you divide by 2. So 3 plus 7 is 10, 10 divided by 2 is 5. 8 plus 12 is 20, 20 divided by 2 is 10. 13 plus 17 is 30, divided by 2 is 15. 18 plus 22 is 40, divided by 2 is 20, and so forth. Yeah? So that's how I get the midpoint here. And of course, the number of P's they give us in the first example here. So all we are simply doing is multiplying the midpoint by the number of P's that they give us in the table. So they will give you this, and they will give you the number of P's. You go and find the midpoint, and all you simply do is multiply the midpoint by the number of P's, and you will get f of x in this case here. And then of course you divide 650 by 40, and you get 16.3 grams. Any questions so far? Yes,
No, sir.
no? Okay, great. Median from ungrouped frequency distributions. So we're going to calculate the median now from a ungrouped frequency distribution. Let's see. So 1 occurred 8 times, 2 occurred 5 times, 3 occurred 9 times, 4 occurred 6 times, 5 occurred 7 times, and 6 occurred 5 times. So let's write that out now. So obviously we write it out here. And we know that the total is 40, right? So half of 40 is 20. So 20 should be in the center. So the 20th score, in this case, if we were to line up everything and list it out, will be 3. So the 20th score is 3, and the 21st score is also 3. Hence, the median score is 3, because if you add 3 and 3 together, you get 6, and divided by 2, you will get 3. You follow?
Yes, sir.
Right. And the reason why we have to add 3 again to it is because 20 is an even number. So if we write out the 40 scores, right, there will be no one particular value in the middle. We'll have 2 values, and the first value is 3 and the second value is 3. So when there are 2 middle values in the median, remember, you add them together and you divide by 2. So that's why I got 3 again here, because 3 plus 3 is 6, and 6 divided by 2 is obviously 3. Okay? So alternatively, the middle class score is n plus 1 over 2. So 40 plus 1 divided by 2 is 20.5. The 2 middle scores are the 20th and 21st scores. Okay, that's an easier way to do it if you want to do it that way. I simply prefer to, I genuinely prefer to just list it out. I could see it better that way. And I know for sure I'm not going to run into errors. Okay, because I don't like to memorize formulas, etc. So I would prefer this long way. Of course, if you prefer it this way, then you can feel free to do it this way, right? N will be the number of persons in the population. So in this case, it's 40, or not persons, well, persons or objects. So 40 plus 1 is 41, divided by 2 is 20.5. So the two middle scores are the 20th and the 21st scores again. So the mode from the frequency distribution. Now you can easily see the mode from this because you can just see the one that occurs the most, right? So for the ungrouped data, the score 3 has the highest frequency of 9, as you can see here. 3, the number of score, the frequency, sorry, is 9. Yeah, indicating that it occurred the most often. So the mode is therefore 3. For the group data, the class interval 13 to 17 has the highest frequency of 12. Let's see here. Yes, so as you can see, 13 to 17 occurred 12 times. So this 13 to 17 score here is the mode. Any questions so far? Okay, so I'll give you all a 10-minute break. We'll resume class in 10 minutes, right? It's now 10:05. We'll start our class at 10:15. So somebody just remind me to unpause the recording, right? To resume, I mean. Okay, let's resume the class. So we're gonna look now at measures of spread or dispersion, right? So before we were looking at measures of central tendency, now we're going to look at measures of spread or dispersion. Now this is also tested a lot in CSEC, so you all should pay attention to it, right? So the first part is the range. How do you calculate the range? The range is basically the difference between the largest and the smallest value in the distribution. So let's see here, the largest value, as we can see, is 88, and the smallest value is 11. So the range is 88 take away 11, which is 77. It's very simple, right? So again, it's the largest take away the smallest. So let's see here, example 10. For the data in a frequency table, determine the range. So anybody wants to give me an idea how we will do this? What is the smallest and the largest scores? How do we get that? Anybody wants to tell me? Do I have to mute everybody, unmute everybody? How do we get it? Everybody's unmute.
How we get what?
How do we get the range for this?
Oh, you plus the largest number and the smallest number.
You plus it as in you add it.
I mean, yeah, minus it.
But what is the largest and the smallest value here? This is a frequency table. What do we have to do here? What's the first thing?
We gotta find the.
We have to find a what?
The mode.
No.
The media.
No.
I don't know, sir. You tell me.
We just did this. You have to find a midpoint.
Oh, yeah.
So what is the smallest midpoint? The smallest midpoint is what? It's from, it will be between 3 and 7, right? So what's between 3 and 7?
Is it 5?
Yeah. And what's the largest midpoint? It will be between what?
23 and 27.
Which will be what?
25.
Correct. Remember, we just add this, we add them and we divide by 2, right? So 3 and 7 is 10, divided by 2 is 5, and 23 plus 27 is 50, divided by 2 is 25. So now to get the range, it will just be 25, take away 5, and we'll get what?
20.
Correct, right? So the range is really 20. Everybody okay?
Yes, sir.
All right. So now we're going to look at quartiles. So it is important to know that when we're looking at quartiles, we're looking at lower quartile, upper quartile, and the middle quartile, which is referred to as the median, right? Now, there's also something called semi-interquartile range. We're also going to be looking at that. I need you all to pay close attention to it because we use it when we are doing cumulative frequencies. Lucky for you, I will just go through the cumulative frequency data, but you all will not be required to draw one, right? But cumulative frequency comes a lot in CXC. Now, it's very easy to do, but I will just go through the theory part of it and not the practical aspect of it, which is drawing the graph, because again, it's a multiple choice exam in this year, 2020, because of the COVID thing. You all know it's a multiple choice exam you're getting, so you don't have to draw anything. So we won't waste too much time going into that. All right. So let's look at the second paragraph. Quartiles divide the set of scores into 4 equal sets. The 3 quartiles are called the lower quartile, denoted by Q1. So you'll call the lower quartile Q1. The middle quartile, which is the median, and you call it Q2. And the upper quartile, we call it Q3. So let's see the following scores here. These are the scores here, right? Of course, if you're given a set of scores, remember it's median you're dealing with, right? So you arrange it in either ascending or descending order. The value that is in the middle in this case is 6. 6 is dead center in the middle as the first value I want to find. So since 6 we know is in the middle, we know 6 is the median. So we call that Q2. Everybody following?
Yes, sir. Yes, sir.
Right. So that 6 splits the score into 2 parts. We have the left-hand side and we have the right-hand side. Now we're going to look at the median on the left-hand side. What is the value in the middle here? In dead center in the middle? The answer is 4. So 4 is now our median on this side. So we call that Q1, which and it's also the lower quartile range. Now let's look at the values on the right-hand side. What is the value that is dead in the center? It's 7, right? So 7 here is the median value of these set of scores here. So this is the upper quartile and we call it Q3. Tell me if you all want me to re-explain that quickly. Okay, I guess everybody good. Now sometimes it is the scores is too much, right? So hence the reason you can use this. So for a larger number of scores, it is best to use a formula to determine the rank of the quartiles. For a set of n scores, n could be any amount of scores, let the location of the ranks of the quartiles be LQ1, LQ2, and LQ3 respectively, right? You don't have to do it like this. You can just do your working and of course get your quartiles, right? So for Q1, it will be n plus 1 over 4, whatever n is. So if n is 40, it will be 41 because it will be 40 plus 4, 40 plus 1, which is 41 divided by 4. That will give you your Q1 value. If you want to find the median, it's n plus 1 divided by 2. And if you want to find the third quartile, right, it will be 3 into n plus 1 all over 4. So this is supposed to be Q3 here, right? So there's a little error there. Be mindful of that when you are doing your work, right? As you can see, it's Q3. So this is supposed to be Q3 here. And how do you find Q3? It's 3 into n plus 1 over 4. Any questions there? People?
No, sir.
All right. Now let's look at the semi-interquartile range. The interquartile range is a measure of the spread or dispersion. It is calculated by taking the difference between the upper and lower quartiles. So in order to find the semi-interquartile range, you have to find the quartiles. Remember I told you all about 4 quartiles. We looked at the lower quartile, we looked at which is Q1, and then we looked at the median, which is Q2, and the third quartile, which is Q3, and now we're looking at the fourth quartile, which is the interquartile range, the semi-interquartile range. And how do you find it? It's found by taking the difference between the upper and the lower quartiles. So the interquartile range, now it's referred to in math as IQR, is the width of the interval that contains the middle 50% of the sample. Now, by ignoring the lower and upper scores, is not affected by the extreme scores. So hence, it is a better measure of the spread than the range itself. So how do you find the interquartile range? It's Q3, which is the third quartile, minus Q1, which is the first quartile, right? Now, if you want to find the semi-interquartile range, you just find half of the value of the IQR. Anybody have any questions there?
No.
That being said, I want you all to find the interquartile range and semi-interquartile range for this data here. Anybody finish it? Okay, so let us see how we will do this then. So we have the scores here. Are you all seeing it?
Yes, sir.
Right. So let us determine what is the median or the middle score. Now, remember I told you all that we can use the formula, right? Let me do it both ways. We'll use the formula. So Q1 is n plus 1 over 4. Q2 is n plus 1 over 2. And Q3 is 3 into n plus 1 all over 4, right? So how many values are there? How many scores are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So Q1 is 16 plus 1 all over 4, which is 17 over 4, which is 4.25 or 4.5, right? That's not, I think I was wrong. (16 plus 1). Let me try the other one. 17 divided by 2, 8.5. That's also incorrect. Okay, hold on. I think I used the formula wrong. See why I don't like these formulas? I prefer the old-fashioned way. 1 minute.
So 17 divided by 4, right?
Yeah.
I get 4.25.
Yeah, me too. But that's not the answer. Okay, here what? We'll just do the old-fashioned way, which I am most comfortable with. I did tell you that at the beginning. So let's see here. Let's eliminate the values. So we have to find the middle value. So we have a value here, we have a value here, one here, one here, one here, here, here. We're trying to determine the middle value, right? So as you can see, we have two middle values here. So when there are two middle values, what do? We add them. And divide by 2. So 19 divided by 2 is 9.5. Agreed? So here is 9.5, which is our median or Q2. Yes, people?
Yes, sir.
So let us see now what is the middle values of the left-hand side and the right-hand side. So what is the middle values here? We have a 4, 8, 4, 7. What else? Oh, sorry, 9. What is the middle value here? So we have 4, 9, 4, 7. Sorry, 4, 8, 5, 7. So we have 5, 6. What is the middle value here? 5.5. Because 6 plus 5 is 11. 11 divided by 2 is 5.5. So this here is our Q1. Let us look at the other side now. So we have 20, then we have 10, we have 11, 19, so, sorry, 11, 19, right? 13, 18, so we left with 15, 16 in the middle. So between 15 and 16 is what? 15.5. So this here is our Q3. Anybody confused about anything?
No, sir.
All right. So we found Q1, Q2, and Q3. Now they're asking us to find the interquartile range. So we already found the interquartile range. And how do you find the interquartile range? Sorry. Remember the interquartile range, IQR, is Q3 minus Q1. So Q3 is 15.5, take away Q1, which is 5.5. Which one give us? Anybody? 10. And if you want to find the semi-interquartile range, remember it's found by finding half of the interquartile range. So it's a half of 10, which is 5. Any questions there?
So I have one question. If the formula don't work out, you do it the long way.
Yeah. The formula didn't work out because I think I did something wrong. But if I go to figure out what I did wrong, I'll take too much time to do that. So that's why I just went the old-fashioned way, which I am accustomed teaching, the old-fashioned way. Now, I'd like to use this formula. I don't like it too much, but because you run into errors and I don't really like formulas. So that's why I prefer the old-fashioned way. I know for sure I will get my answers. Come on, I could take it off, right? Sanjay, who's that in profile picture? Sanjay? Who's that in the profile picture on Zoom?
Dora.
That's Dora looking, so?
As a tutu.
Oh. Okay, I'm taking it off now, right? This is the working for it, but I did it already. Mine was done slightly different. Okay, so median and quartiles from cumulative frequency curve. Right. To determine the median and quartiles from a grouped frequency table, we use a cumulative frequency curve. Now consider the data on scores of students in a test out of 50 shown in the table below. We can obtain estimates of these measures using a cumulative frequency curve, or it's called the ORGIV or ORGIVE, however you want to pronounce it, right? Now, before drawing the cumulative frequency curve, we need to calculate the cumulative frequencies. The cumulative frequency of a particular score X is the number of scores less than X or equal to X. Let me just go straight into the frequency curve, right? Rather than reading all of this. So in the table below, the number of scores is less than 10.5. Sorry, in the table below, the number of scores that is less than 10.5 is 0. The number less than 15.5 is 0 plus 2. So let's see. The cumulative frequency of 20.5 is 7, and we get this by adding the frequencies in turn, and we obtain their cumulative frequency. So the upper class boundary is what? We're looking at the upper class boundary here. So remember I told you, anybody can tell me what's the lower class boundaries for the first one? Anybody?
$5.5.
5.5. Remember I told you it's always 0.5 less than the lower class, right? So the second one, what is the lower class boundary?
$10.5.
Correct, 10.5. So on the upper class boundaries will be 10.5, 15.5, 20.5, then 25.5, 30.5, 35.5, 40.5, 45.5, and 55.5. We are just adding we are just adding 0.5 to the upper class boundaries. Yeah, and that's why I got the upper class boundary of X. Now the frequency, how many times did 10.5 occur? It occurred 2 times. How many times did 15.5 occur? It occurred, sorry, 10.5 occurred 0 times. 15.5 occurred 2 times. 20.5 occurred 5 times, and so forth. Now, how did I get the cumulative frequency? The cumulative frequency is found by adding the frequencies as they come. So the first one is obviously whatever this is. So 0 plus nothing is 0. 2 plus 0 is 2. 5 plus 2 is 7. 10 plus 7 now is what? That's now. Let me snip it and I'll be able to draw and show you all better. Right. Are you all seeing it here?
Yes, sir.
All right. So 0 by 0, 0 plus 0 is 0, right? 2 plus 0 is 2. 5 plus 2 is 7. 10 plus 7 is 17. 14 plus 17 is 31. 9 plus 31 is 40. 5 plus 40 is 45. 3 plus 45 is 48. And 2 plus 48 is 50. Any question there?
No, sir.
Anybody confused? Okay. So let's continue then. So this is how you draw a cumulative frequency curve. We do the following. Determine the upper class boundaries for each interval. We did that just now. We found the upper class boundaries. You calculate the cumulative frequency. I showed you all how to do that just now. Then you plot the cumulative frequency against the upper class boundary of each interval. So the cumulative frequency against the upper class boundary. The frequency always goes on the vertical axis or the y-axis, right? Again, the frequency or the cumulative frequency in this case, it always goes on the vertical axis or the y-axis. And the upper class boundary goes on the x-axis. Hence the reason I put x here, okay? Next, we join the points with a smooth curve. So let us determine the values then. So the points are plotted as 10 point, remember x goes first, right? So 10.50, 15.52, 20.5, 7, 25.5, 17, 30.5, 31, 35.5, 40, 40.5, 45, 45.5, 48, 55.5, 50. These are our values, as you can see here. Now the median is determined by drawing a horizontal line at 25, which is half of 50. As you can see, the total here is 50. So the median will be half of 50, which is 25. So you draw a line, a horizontal line at 25, which is half of 50. And a vertical line from the point where the line meets the curve. In this example, we can see the median score as 27.5. Let us see the example here. Okay? Let me snip it. Right. Are you all seeing it here? You're seeing this, right? Okay, great. So since we know that it is the score, the mark, just give me a minute, right? Sorry. Right, we know the total is out of 50, okay? So where will be the center? Obviously, I told you all just now it's 25, right? So we locate 25, 21, 22, 23, 24, wait, 20, 22, 24, 26, so 22, 25 is here. So we draw a horizontal line and then a vertical line coming down. So everybody can tell me what is that value there? Let me do it back properly. Somebody say something in the chat. Yes, correct, 27.5. So 25, each bar represents 2, right? So 25, 22, 24, 25, and this is 28. So between 25 and 28, sorry, 26 and 28 is 27.5, right? Yeah. So we just found the median. Now, in a similar fashion, we will find the other points, which is the 3 quartiles. So how do we find the other quartiles, people? Anybody? Anybody wants to volunteer and tell me? Gina, you want to help? Okay, so how did I find the median? The median, remember, it's half of the range, right? Sorry, the entire thing. So the lower quartile range will be what? And a quarter of it. So what is a quarter of 50? A quarter of 50 is how much? How much is a quarter of 50? 12.5, very good. So we'll go now at 12.5. So between 10, this is 12, 12.5 is here. And we draw our line going across. And then we have a line coming down. So what do you all think is that value there? Let's find our third quartile. What is 3/4 of 50? This is around 23.5 or something, right? Let's find 3/4 of 50. That will be around here. You all have to know how to do this, huh? So this is around 32.5 as well. Yeah? Any questions so far?
No, sir.
Okay. So let us now look at standard deviation. All of the things that I'm leaving out, you all can read it, right? That's just data for you all to read. Let me just show you how to find standard deviation. Or you can read it on your own. I'm just trying to finish all the handout, right? So let me go to the camera.
So that standard deviation, that not in maths anymore, or that's still in maths?
Sometimes they ask, I've seen it in the multiple choice.
No, because my teacher was saying that how it not in maths now, it in add math.
Yeah, it's no longer in maths, but I've seen questions that talk about the standard deviation. That's why I'm going to do it still. And that's why I'm not going to read the note for you. I'm just going to show you how to find it. Because it's not difficult to do. So let's say you have a set of scores x, such that x is 4, 0, 6, 8, 5, and 7. The first thing you have to do is find the mean. So x bar, right? How do we find the mean? Remember, it's 4 plus 0 plus 6 plus 8 plus 5 plus 7 divided by the total number of scores, which is 1, 2, 3, 4, 5, 6. So this will be what? Let's add it up. 4 plus 6 plus 8 plus 5 plus 7. That's 30 divided by 6 is 5. So the mean is 5. Any questions so far?
So that thing with the x and then the line on top x, that is standard deviation.
No. That's the symbol for the mean. It's called x bar. So we have x here. Then we list our scores. So our scores were 4. Well, we were put in ascending order, right? So 0, 4, 5, 6, 7, 8. Okay? These are our scores that we get from the top here. Now it's x to the standard deviation, sorry, to the median, the mean, sorry. So x is 0, 4, 5, 6, 7, 8. So it's x take away the mean. What is the mean? 5. So take away 5, 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 take away 5. All right? This next column here is x take away the median, sorry, the mean squared. So 0 take away 5 is -5, and -5 squared is 25. Any questions or concerns so far?
No, sir.
Okay, so 4 take away 5 is -1. So -1 squared is +1. 5 take away 5 is 0, 0 squared is obviously 0. 6 take away 5 is 1, 1 squared is 1. 7 take away 5 is 2. So 2 squared is 4. 8 take away 5 is 3. 3 squared is 9. And of course, if we add up all of this, 25 and 9 plus 4 plus 2 is 40. And that's it. Any questions there? I'll leave it up for a minute for you all to take it down. And next we're going to move on to probability, right? Actually, Shushmita, I'm now checking the syllabus. It's still here. Standard deviation. That's why I see it. You hear me?
Yes, sir, I hear you.
Yeah, it's on the syllabus still. But the only thing about it is you are not required to do any calculations for it. So basically, you will have to read off data from the information given based on the standard deviation. So yeah, I just wanted to double check that to make sure I didn't teach her something that's not on the syllabus.
No, so it's just a teacher and she said then they on the syllabus, so that's why I asked you now about it.
Oh, no, it is on the syllabus. It is.
Thanks.
No problem. So we are almost finished, right? So let's go back to the handout now. All of this is for standard deviation, Shushmita. But all of this, we don't need to teach you all. This is what actually you all have to learn how to read off based on the information. So when I send you all the handout, I hope you all go through it and try to read it. But in CXC, more or less, you will be given a diagram and have to read off the standard deviation from it. Yeah, no calculations are required, but it's still on the syllabus. So let's move on to probability now. We often encounter situations in which we need to take a chance or risk, and we are faced with a set of options. The study of probability gives us the tool to make informed decisions about areas in life. Where there is a degree of uncertainty, it teaches us to consider all possible conditions and the relative importance of each one of our final outcome. We begin by learning how to calculate the probability of events that occur in simple experiments. So the probability scale. Probability is the measure of how likely an event is to occur. In mathematics, we quantify measures by assigning some value to it. In constructing a probability scale, we can think of two extremes. What is the probability of an event that will never happen? This is an impossible event. It is assigned the smallest possible value of 0. So let's read this again. When the probability of an event that will never happen occurs, we put 0 as the value assigned to it. The probability of an event that is certain to happen, it is assigned the largest possible value of 1. So if it's not going to happen, 0. If it's definitely going to happen, and you're strong about that, you think it's really going to happen, you assign the value 1 to it. Hence, for any event, the probability will always lie between 0 and 1. No value of probability can ever be negative or greater than 1. Any questions there? This is very important. You can't have a negative value, or you can't have a value greater than 1. Okay? Let's look at some examples here. So we can think of the probability scale as a number line with values only in the interval between 0 and 1. So impossible, possible. 1 is possible or certain to happen. If it's uncertain, it'll be 50-50 or half. Right? Any questions? In the middle of the scale, the probability is 1/2 and will correspond to events that have 2 possible outcomes, either which is equally likely to occur. Examples of such events are getting a head when flipping a coin or using a red card from a deck of playing cards. These events are said to have 50% probability of occurring, and so there is a 50-50 or even chance of either outcome to happen. So I want you all to notice that the probability can also be represented by a percentage, as you can see here. Yes? Now, terms in probability, some of the terms include experiments, outcomes, impossible event, an event that's certain to happen, an event that is very likely to happen, an unlikely event, etc. Okay, so let's see. An experiment is a situation involving chance or probability. The possible results of an experiment will be called the outcomes. An impossible event is one that will never occur. So for example, a rose bush growing from an apple seed is an impossible event. A certain event, which is one that will definitely occur, is the sun rising every morning. Now this is a certain event. You know it's going to happen for sure. An event whose probability is close to 1 is called a very likely event. So for example, the probability that a teenager will own a cell phone is very likely. So that's a very likely event. It's not a certain event because you're not sure your parents going to purchase you a phone. So it's not a certain event. A certain event is something that you know going to happen regardless of what takes place. So for example, the sunrise, that's a certain event. A very likely event will be an example with a teenager getting a cell phone. Okay, we're not sure that that's going to happen. Or the likelihood of a teenager reaching puberty or of a child reaching puberty. We're not sure that child is going to live. It's a very likely event that the child will live, but it's not a certain event that the child will live because of factors such as crime, health problems, among other factors, right? It's not certain, but it's very likely that the child will reach puberty. An unlikely event is an event whose probability is close to 0. So for example, buying a winning ticket in the lotto. You're not sure you're going to win the lotto. So it's a very unlikely event and your probability will be very close to 0. So in this scale here, your probability will be somewhere here of winning the lotto. Okay? Let me see who's online. I'm not hearing from them. Johnson, I ain't hearing from you. Say hello if you're there.
Hello. Hi here.
Hey, you're real quiet, girl. Let's see who else is online. I know Nitu is online. I've seen her replying and stuff. Rihanna, are you here?
Yes, sir.
I hear your voice a couple times.
Yes, sir.
All right, I'm not Jada here. Felicia, are you here? Felicia?
Yes, sir.
Okay. Felicia, how do you pronounce your last name?
Pengoshe.
Oh. If you check me trying to pronounce that the first day, Bengochia and all kind of craziness. It's French.
Spanish.
Eh, oh, my bad. Thank you. All right, so let's continue then. So let's look now at measuring probability. To measure the likelihood that an event will happen in simple experiments, we consider the conditions that affect the outcome, and we use a fraction to compare the number of favorable events to the total number of events. Okay? So let's see. If E is an event, then the probability of E occurring is written as P of E. This is read as P of E. So P of E is defined as the number of outcomes that are favorable to the event over the number of possible outcomes, or we can see the number of ways that the event can take place over the number of possible outcomes. Yes? So let us consider how this definition applies to calculating the probability of an event. The diagram below shows a spinner wheel with 4 equal size sectors, differently colored, such as yellow, blue, green, and red. An experiment of turning the spinner will result in the arrow pointing in one of the regions, either red, blue, orange, or green. Now, since all the regions are equal in area, all 4 outcomes are equally likely And so the probability of the spinner landing on any color is the same. Not following?
Yes, sir.
So in this example, the experiment is spinning the spinner. And outcome is the result of any single trial of the experiment. A trial will comprise one turn of the spinner. The sample space is the set of all possible outcomes. The experiment has a sample space of 4 outcomes. It can be either red, blue, green, or yellow. And an event consists of one or more outcomes of an experiment. So for example, one event of this experiment landing on blue, an event is landing on blue or red. We know that the total number of possible outcomes is 4. So we can have yellow, blue, green, or red. So we can now calculate the following probabilities. So let's say you were asked, what is the probability of landing on blue? Anybody wants to tell me that? What is the probability of it landing on blue?
1 out of 4?
Correct, 1 out of 4. What is the probability of landing on blue or red? Anybody? 2 out of 4, correct. Yes, Emily, you are correct. Because remember, it's blue or red. So it's either or. So it's 2 out of the 4, which is a half, right? As you can see here. So equiprobable or equally likely events now. In tossing a fair coin, which is either heads or tail, the probability of getting heads is the same as the probability of getting tails. In the same way, rolling a fair die, the probability of getting 6 is the same as the probability of getting 1, 2, 3, or 5. Such events are called equiprobable events or equally likely events. Anybody can think of any others? You can think of any others? Okay, all right. If, however, the die or coin is weighted, sometimes called loaded, the outcomes will not be equally likely. In such a case, we refer to the coin or die as biased. Otherwise, the coin or die is said to be ordinary or fair or unbiased. So if you use a regular die, which is called a fair die or a normal coin, it's called unbiased. You can call it fair, ordinary, or whatever. If, however, you do something to the die to manipulate it to get a desired outcome, it is referred to as biased, okay? And it's not fair, it's unfair. You will not get a fair chance of getting a particular number. So 3 common experiments involving equiprobable events are described below. A fair coin is tossed. There are 2 possible outcomes, heads, which is H, and tails, which is T. The probability of obtaining a head is P of H, so that's the probability of obtaining head, and the probability of obtaining tails is P of T. So what is the probability of obtaining a head? It's 1 out of 2 chances, and the probability of obtaining a tail is 1 out of 2 chances. In each case, there is 1 favorable outcome out of 2 possible outcomes, either head or tail. Now, let's say a die is tossed. What is the probability of obtaining a 1? 1 out of 6 chances. The probability of obtaining a 2, 1 out of 6 chances. The probability of obtaining a 3, it's 1 out of 6 chances. All of these are 1 out of 6 chances. Now, suppose that A is an event that an even number is obtained. Then how many even numbers are there? Let's see. 2, which is 1, 4, which is another 1, and 6, which is 3. So there are 3 even numbers. So the probability of obtaining an even number is 3 out of 6. Any questions here?
No, sir.
No,
So
sir.
what is the probability of obtaining an odd number?
Three out of six.
Correct, 3 out of 6. And the odd numbers will be 1, 3, and 5. So a card is picked from an ordinary pack of playing cards. Q is the event that a queen is obtained. Now there are 4 queens in a pack of 52 cards. So the probability of choosing a queen is 4 out of 52. And of course, if you want to reduce your fraction to its lowest form, you'll get 1 out of 13. Anybody have any questions so far? Okay. Impossible and certain events. An ordinary fair die is tossed. Find the probability that a 7 occurs. So it will be the number of 7s on a die over the number of possible outcomes. Yeah? How many 7s are there in a die? None, right? So 0 out of 6, which will give us 0. Agreed? Yes, people?
Yes.
Okay. Now we can think of other impossible events. Say, for example, a card is chosen at random from an ordinary pack of playing cards. The probability that the card is green is impossible since all of the 52 cards in an ordinary pack of cards are either red or black. So an ordinary fair die is tossed. Find the probability of obtaining a whole number. All of the numbers are whole numbers. So the probability of obtaining a whole number is 6 out of 6, which is 1. And 1 represents that the event is certain to happen. Remember, it can be between 0 and 1. So since we get 1, we know that it is certain to happen. Any questions here?
No.
All right. So a month of the year is chosen at random. Find the probability that it has more than 27 days. So P will represent the number of months that has more than 27 days. Now, all of the months have more than 27 days. So it's 12 out of the number of months, which is 12, which is equal to 1. So this event is certain to happen. Yeah? Any questions so far?
No, sir.
All right. Laws of probability now. We are now in a position to formally state the laws of probability. Now, the first law states that the probability of an event P of A, it must lie in the interval 0 and 1. It can be equal to 0, or it can be equal to 1, or it can be less than 1 or greater than 0. That's what this is telling you here. The sum of the probabilities of all the outcomes in a sample space must total 1. And the third one, if 2 events A and A prime make up a sample space, then the probability of A prime is equal to 1 minus the probability of A. Any questions? Okay. So a card is drawn at random from an ordinary pack of 52 cards. S represents the event that an ace is obtained. Calculate the probability of not obtaining an ace. What is the probability? How many aces are there in a pack of cards? Four, correct. So let's see the working here. The probability of obtaining an ace is 4. So 4 out of 52, which is 1/13. And remember, if you want to find P of S prime, it's 1 minus the probability of S. So 1 minus 1 out of 13 is 12 out of 13. Any questions?
No, sir.
So let's look at an example here, another example. The probability P of R of rain tomorrow is given by P of R is equal to 5 out of 7. Calculate P of R prime, the probability that rain will not happen tomorrow. Remember, R prime will be 1 minus P of R. So 1 minus 5 over 7 is 2/7. Stop me if you all have any problems, right? Are we good? Let's look at an example. A company inspector found that 3 in every 100 bulbs manufactured are defective. What is the probability that a bulb is defective? Anybody?
True over 100.
Correct. Right? Because the number of defective bulbs is 3, and the number of bulbs in the sample is 100. So it's 3 out of the 100. Now, how many bulbs are expected to be defective in a shipment of 2,000? I want Johnson to answer this. Johnny. Johnson area?
Messageri answer.
What's that?
A messageri answer.
Yeah, you're correct, Sanjay. But I want to see Johnson will share the answer first. Okay, Sanjay, go ahead and share your answer.
60.
Well, yeah, tell me how you get the 60.
3 divided by 100 multiplied by 2000.
Yes, correct. So remember, the probability of the bulbs not working is 3 out of 100. And if you manufacture and you shipped 2,000 bulbs, then it will be 3 out of 100 multiplied by 2,000. And that will give us 60 bulbs. Yeah? Try this example now for me.
One fifth.
Yeah, how you get that?
Divided by 6.
Okay, so here we are seeing terms such as experimental probability and theoretical probability. Now, what is a theoretical probability? A theoretical probability is more or less an event that we can predict. Okay, we sure we can predict it. Yes? Now, an experimental event is the value of a probability that we more or less receive from conducting an experiment. Yeah? So based on the data, what is the experimental probability? Here we can see that, what is the experimental probability of tossing a 4? Here we can see that the frequency of tossing a 4 is 6, right? So how many times you would have tossed the dice? You all think we could have tossed the dice? How many possible times? It will be 3 plus 6 plus 4 plus 6 plus 4 plus 7. So we add up all of the numbers in the frequency, and that's how many possible times we could have tossed the die, which is 40 times. So 6 out of those 40 times, sorry, 30 times, yeah, my bad. 3 plus 6 plus 4 plus 6 plus 4 plus 7 is 30 times. So the number of times you would have conducted the experiment would have been 30 times. Now 6 out of those 30 times, you would have obtained the 4. So the probability of obtaining a 4 will be 6 out of the 30 times, which is 1/5. Now, what is the theoretical probability of tossing a die and getting 4? Remember, the theoretical possibility will refer to the predicted amount of time. We know for sure that out of the amount of how much of amount of tries we get, that we must get 4 at least one time, right? So the theoretical probability of obtaining a 4 is 1 out of the 6 times. Sorry, 1 out of the 6 faces of the dice. Yeah? Anybody confused about anything?
So
Okay, so let me just explain mutually exclusive and exclusive events, and then we shall end class for today. So mutually exclusive events. 2 events are mutually exclusive if they cannot occur together. This means that they have no common outcomes or they are disjoint. Some examples of mutually inclusive events are tossing a coin and the outcomes head and tail cannot occur together, right? So that's an example here. You cannot toss a coin and get heads and tails together. One has to happen, not the 2. Tossing 3 coins, the 8 outcomes in the sample space are that you can get head, 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 tail, tail, tails, head, tails, head, tails, tails, head, tails, tails, head, tails, and tails, head, head, or tails, tails, head. You can get any one of these possibilities if you toss 3 coins. You cannot get anything other than these possibilities here. Okay? The third one, tossing a die. The 6 outcomes include 1, 2, 3, 4, 5, 6 in the sample space, and they are mutually exclusive. Now, you cannot get a 1 and a 5 occurring at the same time. Only one on the top is the one that's counted. Okay? You can't have 2 or more numbers occurring at the same time. Selecting an ace or a jack from a deck of playing cards, these 2 events are mutually inclusive since no card can be an ace and a jack at the same time. You can either pull an ace or a jack. You can't pull a ace jack or a jack ace. It's nothing like that, right? However, the event selecting an ace and a black card is not mutually exclusive because these events can have common outcomes. the set of aces contain 2 black cards. So they are not mutually exclusive. You all following?
Yes, sir.
All right. So in rolling 2 dice, the events, the sum is 4, and the event at least 1 is 5, are also mutually exclusive because there are no outcomes common to both of the events. Now the diagram that I'm going to show you all, it will show that the 36 outcomes with the event, the sum is 4, shaded in red, and the event at least 1 is 5 is shaded in green. Right? I want you all to notice how disjointed the sets are. Right? There is nothing really common in them. Now let's look at the addition law for mutually exclusive events. Now you all don't really have to learn all these because I don't really see them coming, right? Yeah, but I'll still go through it and I'll just go through the addition law. And that's for mutual events and non-mutual events. Okay, and you all will read up the multiplication law on your own, right? Because I hardly see that one ever coming. So the addition law for mutually exclusive events. Consider the experiment tossing a die. We wish to determine the probability of getting a 6 or a 2. This can be done by simply applying the definition of probability. There are 2 favorable outcomes out of a total of 6 outcomes. So P can be either 6 or 2. So it's 2 out of 6. Alternatively, we could have obtained the answer by combining the probabilities of the 2 events, as shown below. P of 6 is 1/6, and P of 2 is also 1/6. 1/6 plus 1/6 is 2/6. Any questions?
No, sir.
Okay, so let's consider an experiment now with tossing 3 coins. We wish to determine the probability of getting 3 heads or 3 tails. In the sample space below, we can see how many times the outcomes can occur. Yeah, so 2 favorable outcomes of 8 outcomes will be getting 3 heads or 3 tails. So it will be P of 3 or P of T. So how many times we can get 3 heads? 1 out of 8. And how many times you can get 3 tails? 1 out of 8 as well. So 1/8 plus 1/8 is 2/8. As you can see in the bottom here, you're waiting for it. Any questions?
No, sir.
Okay, so in the above examples, we were calculating the combined probability of 2 mutually exclusive events using 2 different methods, right? And of course, we will have been yielding the same results. We saw the addition rule is more efficient because it did not require us to list the entire sample space. In practice, we do not always have knowledge of the sample space. And so the addition rule is very useful in calculating the probability of mutually exclusive events. So let's see the addition law for mutually exclusive events. So P of E or P of F is equal to P of E plus P of F. Now, P of E intersect F is equal to 0. There is no intersection because I remember telling you all that they are disjointed. Remember I told you all that they are disjointed, so there is no intersection. Okay? So here's an example for you. It is known that the probability of obtaining 0 defects in a sample is 0.34, whilst the probability of obtaining 1 defective item in the sample is 0.46. What is the probability of obtaining either 0 or 1 defective item in the sample? So let us see here. We can let E1 be obtaining 0 defects and E2 be obtaining 1 defective item. So P of E1 is 0.34 and P of E2 is 0.46. Now remember I told you all it's P of E1 plus P of E2. So we just simply add them. So 0.34 plus 0.46 will give us 0.8. So the probability of obtaining either 0 or 1 defective item in a sample is 0.8. Now this will be very close to 1. So the event of obtaining 0 or 1 defective item in the sample is very likely or highly likely. Or it's a likely event. You all following? Yes, no? Oh, John. All answering?
No.
No what?
Yes.
Okay. So the addition law for non-mutually exclusive events. So the addition law for mutually exclusive events stated above is a special case of the general addition rule in probability. The general addition rule applies to both mutually exclusive events as well as non-mutually exclusive events. It is related to the following law in set theory when we have two intersecting sets. So the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. So this is in the set theory handout. If we divide each term by the total number of outcomes in the sample space, we obtain the exact same thing here. So for mutually exclusive events, the number of elements in for mutually exclusive events, P of the intersection of A and B is equal to 0. In this respect, the law holds for both types of events. That's when there's an intersection occurring here. Okay? So let's see how we're using this law. A single card is chosen at random from a standard deck of 52 playing cards. What is the probability of choosing a king or a club? Now remember, there is a king of clubs. So this is not something that is impossible, right? It is possible. So P of the king will be 4 out of 52. So we can choose 4 for the kings out of the 52 cards. And how many times we will be choosing a club? There will be 13 clubs out of the 52 cards. So it's the probability of choosing a king, which is 4 out of 52, plus the probability of choosing a club, which is 13 out of 52, minus the probability of choosing a king and a club, which is 1 out of the 52. Okay? So this will give us 16 out of 52, which is basically 4 out of 13. Now I'm going to give you all an example and I want you all to try this and then we'll end class. Okay, I'm giving you all 2 minutes to try it. So in a maths class of 30 students, 17 are boys and 13 are girls. On a test, 4 boys and 5 girls made an A grade. If a student is chosen at random from the class, what is the probability of choosing a girl or an A student? So what is the probability of choosing a girl? I'm unmuting everybody. I want you all to answer me collectively. The probability of choosing a girl.
5 out of 13.
Choosing a girl? No.
Yeah.
The probability of nope. The probability of choosing a girl is 13 out of 30.
Oh.
Yeah.
So 13 divided by 30.
And what is the probability of choosing a boy?
17 over 30.
Correct. Now the question tells us here that on a test, 4 boys and 5 girls made an A grade. So what is the probability of students making an A grade? And it's 4
5 out
plus,
of 30 for girls and 4 out of 30 for boys.
right? So what's the total probability of students making a grade A?
9 over 30.
9 out of 30, right? So the probability of girls is 13 out of 30, and the probability of getting an A grade is 9 out of 30. Now, what is the probability of a girl getting an A grade? And 5 out of 30, we see that any question here?
Yeah.
Right. So the probability of a girl getting an A will be the probability of girls, which is 13 out of the 30, plus the probability of getting an A, which is 9 students out of the 30, right? And we're taking away all of that. We're taking away the probability of a girl getting an A, which is 5 out of 30. So let's see the working here. Right, you all can see the working here. The probability of choosing a girl is 13 out of the 30. The probability of choosing an A student, remember we had 4 boys and 5 girls getting an A. So the probability of getting an A grade is 9 out of 30. So the probability of a girl getting an A is 5 out of 30, which was also stated in the question. So the probability of a girl gets, or the probability of a grade A will be the probability of a girl, which is 13 out of 30, plus the probability of getting an A, which is 9 out of the 30. And we take away, from that, we take away the probability of a girl getting an A, which is 5 out of 30, thereby allowing us to obtain our answer of 17 out of 30. Any questions there?
No, sir.
Okay, well, in that case, that brings us to the end of our class for today. I hope that you all learned a lot from it. If you all have any questions, feel free to let me know, okay?